Good morning. Here we are at the physics video lecture. Once again, it is Physics 105A, video lecture 30. We are working on central force problems, and I'm going to begin actually with an announcement while I still have your attention. And the announcement concerns next semester. I want to offer a 1-unit class that goes along with 105B. So for 105B, a 1-unit recitation course in which we just solve problems together and the students go to the board. It's absolutely the best thing that I can offer you. So I highly recommend it. I'm also going to send out an email with the same content. I hope we get everybody on board to sign up for this 1-unit recitation course. And it would be in the form of an independent study, and the time would be set up later. Okay, so first of all, I would just have to have your commitment to that. So it would be as an independent study. That's just formal though. It's 1-unit class. And I could also include some more material on complex numbers, complex functions actually. So it goes with 105B, possibly also complex variables, where we could continue some of the material we've taken up in this semester and go a lot farther with it. Complex functions. Okay, so give it some thought. I hope we get all of us on board. It's going to be great. It's really the best thing. Students do really well with this, and it builds you up immensely. Good. So that has been said. What we're doing now is the central force problem. I'll review a bit of what we have done and then tell you where we're headed with it. So first of all, when you have a central force, it's a problem that looks like this, where the force, we're now in free space, it's a function of position. The potential energy exists when this integral here is unique, or path independent, I should say. But dr prime, and the argument of the potential energy is up here. That's just some arbitrary point. And we have to have curl of, this gives us, so that gradient of u of r is equal to minus our force, and the condition for that is that the curl of this vector vanishes. Good. And, so condition for that let's say necessary and sufficient. Curl of f is equal to 0. So we've talked about that. So the next step we had is that our central force has this form. It's a function of r times this unit vector. This unit vector just gives the direction. It's directed away from the origin. And this r here is the magnitude. How about I just write the magnitude of r which in free space here, x squared equals y squared plus z squared. We did a little calculation with this. I assigned something. Okay, where we're headed with this is a one body problem, right, with one mass. But what we want to solve is the so-called Kepler problem. And we're going to head straight there. But the Kepler problem is a two-body problem. So next, the two-body problem, the general two-body gravitational problem, which reduces, it turns out, formally to a one-body problem. That's what we're going to tackle. So here's what we're going to do. Two-body problem reduces to I'll write formal just to indicate that there's something going on there. One body problem, which is this right here. Okay. And once we've done that reduction, then we can talk about different forces and in particular Newton gravity. Okay. So then central forces. We know we certainly have at least two of them now. We already talked about the R squared potential energy last time, and of course we're going to have the 1 over R squared Newtonian gravity. So central forces, and then in general, and then Newtonian gravity. So we'll begin with this two-body problem. I should state that next semester we'll be talking about a more general case where we would have n bodies, okay? But right now we'll just go ahead with 2-point masses in space and develop formalism through to this equation right here. So this we have to set up with some vectors. So two bodies, 2-point masses, M1 and M2, and we'll just go ahead and locate them right here. Origin somewhere. So this is the vector R1, this is the vector R2. This is M1, this is M2, and the first thing we do is define this relative vector. R is equal to R1 minus R2. So that's the relative vector, doesn't get a subscript. And then we're going to take a center of mass. I always like to draw a little star at the center of mass, M1 and M2. So we suppose the center of mass is right there. We have R center of mass, M1 R1 plus M2 R2, divided by the sum of the two masses. And what we're going to do is express these two vectors with respect to the center of mass. What we want to do is have the center of mass be the origin. So this is the center of mass. Now express R1 and R2 in terms of, with respect to the center of mass being the origin. Or center of mass as their origin. So what we have there, if that's supposed to be the origin, we have this numerator is going to vanish. Okay? So the numerator here vanishes. That tells us, that takes the center of mass being 0, being the origin. So we have m1 r1 plus m2 r2 equals 0. We have that equation, and we have this definition with the difference vector here, r. Or so we can say m1, and we'll just solve for r1, that's r plus r2, r plus r2 plus m2 r2 is equal to 0. Coming up to here, so now we're going to solve for r2. So we have m1 plus m2 times r2, m1 r2 equals minus m1r, and there we go. r2 is equal to minus m1r divided by m1 plus m2. And just by reversing the letters and recognizing that R1 will be in the direction of R, we can immediately say, and R1 is equal to M2R divided by M1 plus M2. So there we have the result. Still the same 2 points in space, we've just taken the center of mass as our origin. We'll go ahead and put a box around these. You can always derive these with no problem. Good. So what we're going to do next is write down Newton's law for each of those two particles. And now we're going to bring into play Newton's third law, which we haven't really had any reason to discuss up until now. So, Newton's second and third laws for the two-particle system. We have, just kind of write them out, m1 r1 second derivative is equal to force on 1, and m2 r2 double dot is equal to f2. But what we do know is that these two forces here, since it's the interaction between those two particles, are equal and opposite, with F2 is equal to minus F1 is equal to minus F is equal to minus, well, we'll get, actually, let's leave it right there for now. We can ditch the subscript because it's equal and opposite sign. Okay? So then we can write m1 r1 second derivative is equal to f m2 r2, second derivative is equal to minus f, where it's the same, right? Same magnitude, opposite direction. Okay, so far so good. Now what we're going to do next is what I was mentioning earlier, this reduction of a two-body problem with two vectors here, 6 components, to a one-body problem. So what we do now, let's just call this star here, is multiply the first equation by m2 and by the second equation by m1 and subtract them from each other. So here's what I get. So from this thing here, I'll do it. We have m2 m1 r1 second derivative minus m1 m2 r2 second derivative. I have to go over to what the right side was. That was m2 f minus negative m1 f. So that's just, like I said, multiply this one by m2, this one by m1, and subtract them from each other. What we get is m1, m2, r1, second derivative minus r2, second derivative is equal to m1 plus m2 times this central force F between the two masses. I haven't actually made use of the fact that it's a central force yet. I was about to, but I just held off. So it's just the equal and opposite force. But here's the interesting thing. We now have this difference vector. Here we go. So this r is r1 minus r2, so its second time derivative is the difference of those two second time derivatives. So I'll just note that just so it doesn't get lost in the mix. R double dot is equal to R1 minus R2. So we have M1, M2. And then I'm going to divide both sides by M1 plus M2. So what we have is M1, M2 divided by M1 plus M2. Second derivative of the difference vector is equal to F. And these forces were forces of position. But I'll fill those details in a moment. But we essentially have what I had advertised there. We have the same form. We have reduced the problem to a one-body problem, and this complicated looking mass here gets a special name. It's referred to as the reduced mass. I'm going to write that down as a 2. Okay. So this is going to get a name. In fact, I'm just going to call it lowercase m again. Then we'll have this here, and then we'll have the force between the two objects. Okay. Which will therefore also, because it's a force between those two objects, it'll be a force as a function that's a function of this difference vector. So we've achieved what we set out to do. And I'll send this up and then rewrite it. So there's the definition of these R1 and R2. So this is interesting. You solve this problem, and then you can come back when you're all done, and you can just find what those two individual motions are, but they're going to be highly correlated, right? Because they're just different constant multiplying each one. Okay. So yeah, we have this differential equation to solve, and those are the definitions that are in there with the two individual vectors. And if you have orbiting bodies, you're going to have them orbiting their common center of mass, right? We already know where we're headed in that regard. Good, so let's go ahead and clear up some space here. So we've reduced the two-body problem to formally a one-body problem. So continuing this thing here, the reduced mass, that's what we call this, M equal to the product of the two masses divided by their sum. Okay, so that's the reduced mass. And just to immediately give an important example, you have a smaller body, say some satellite, orbiting a larger body. Right, we're headed that way. So that's M, and that's capital M. And this is M1, and this is M2. Okay. So what happens to the reduced mass in this case? Or what does it mean? Okay, those are the antenna of our satellite. Okay. So for this example here, M equals product. Gotta use a different letter, huh? Forget the upper and lower case. It's going to just run into trouble. We'll do that later. We're just going to call them M1 and M2. Okay. With the understanding that one is a lot larger than the other. So here, we've got our reduced mass. So we have one that's much larger and one that's much smaller. So we've got this M1, M2 over M1 plus M2, but the M2 is much larger, so that's right, M2 times 1 plus M1 divided by M2 in the denominator. That's M2 plus M1 again, but since one's much larger, I pulled that M2 out. I do that, you can see I can cancel here, and I have M1 over 1 plus M1 over M2. But this is much, much smaller than 1 here, so that's approximately equal to M1. So the reduced mass, if you're orbiting a very large body, is really close to, but not exactly the original one. Okay. That's an important example to realize that, and it's reduced because it's slightly smaller, right? Because it's 1 plus something there. And what else? Oh, very interesting anecdote. So this central force problem isn't just, say, the moon around the Earth or the Earth around the sun. When you move on into atomic physics, it's the electron around the proton. And the story I heard a long time ago was that when Niels Bohr did his original calculation for the Bohr model of the hydrogen atom, he just plugged in the electron mass, and he was off by, 1% or so, some very small number. But then when he put in the reduced mass for the electron-proton system, he just nailed the example exactly. Someone told me, I'm telling you, but it definitely shows you the importance of the reduced mass. Good. So that's the reduced mass, and we are right here. So we're just going to rewrite this equation now. So we're back. So in fact, we're back to our central force equation as we had it before. I'll go ahead and erase this board. You guys have this. So what do we have now? Now, with the reduced mass, M only difference being that we recognize this as the result of a reduction from two bodies to one. This is the difference vector, and this is the magnitude of the difference vector, and we're talking about a central force. So I can write here, now we have this again, and we are ready to start developing the formalism here. So we have this, and we already know about potential energy with U of R equals minus integral R prime dr prime. And given this, we have conservation of energy. So I'll write and 1/2 m r dot squared plus u of r is equal to E. So that's the one conservation law. There's another conservation law in the central force formalism that we have to get to before we can begin solving this problem systematically. So next, consider this expression here. L is equal to R cross M R dot. That's the angular momentum. The really systematic discussion of these conservation laws actually comes next semester. So right now I'm just introducing it as I can, but I'll say that it's the angular momentum. What we do now is take the time derivative of this. dl dt, and we just have a product rule, so that's R dot cross M R dot plus R cross M R second derivative, right? We just took the time derivative product rule. We discover something interesting. R dot cross R dot, and it's just a scalar, parallel vectors. Okay. So cross product of parallel vectors vanishes. So that's 0. This one here is interesting as well because I'll just keep the equal sign going. So we've got the 0. We've got R cross MR second derivative, which we can substitute F of R divided by its magnitude. And we have just found that we have the same thing. That 0 is just getting in the way, so equal, right? This was 0, we dropped it. So yeah, we can pull the F of R over R here out. We have R cross R again. Cross product with itself vanishes. So both of these vanish. Therefore, the whole thing vanishes, and this is a conserved quantity. So the central force problem has a conserved angular momentum without saying anything else about the form of this. The angular momentum is guaranteed to be conserved. So L is constant with respect to time. Angular momentum is conserved. So we add that to our properties here. We have, central force problem, we have potential energy, we have energy being conserved, and we also have the angular momentum being conserved. We're going to do a little calculating with this conserved angular momentum. But the angular momentum is a vector. It's a vector, and position and velocity are both perpendicular to the vector. That is to say, this vector here is perpendicular to the plane that is spanned by r and r dot. Because it's constant, it doesn't move, so it's perpendicular to these two vectors. In other words, these two vectors must live in a plane because of the constancy of the angular momentum. So that's another property we've just gained. Go ahead and erase this whole board. So important note. L is constant in direction, it's a vector, and magnitude. The fact that it is constant direction means it's perpendicular to a plane. And that plane is the plane in which r and r dot are found. Therefore, the motion, right, these characterize the motion, so the motion takes place in a plane. For the motion, central force motion, this is the important consequence, central force motion, what we'll call it, is restricted to a plane. Okay, now it's restricted to a plane. That's going to inspire us to use plane polar coordinates. So all that work we did earlier in the semester with the plane polar coordinates will pay off. So we use plane polar coordinates. And doing that, we can get an interesting expression for this vector L here. Let's go ahead and try to write the vector L in plane polar coordinates. So we have L is equal to R, and remember, I'll write the definition out. R cross M R dot. So remember, in plane polar coordinates we had magnitude times the unit vector, and we're going to cross that into M times R dot. And you'll remember, or you'll have to look it up, but we've done it, the velocity vector in plane polar coordinates was R dot R hat plus R phi dot phi hat. Okay. So what is this when we take that cross product? I'll do it down here. Well, we've got, let's just multiply it. We have R M R hat cross R hat. Of course, that's going to vanish. I'm just writing it out because I can. Plus R M, and we'll have the R hat. Okay, so R, here I didn't write that out correctly. Let's make sure we do that right. We have R M R dot R hat cross R hat plus R M R phi dot R hat cross phi hat. So yeah, this is going to vanish, right? R hat cross R hat, that's 0. This will not vanish. In fact, this will be M R squared phi dot, and the R hat cross phi hat, let's do our little picture. X, Y, here was the phi, R hat, and phi hat, as you guys may remember, right? Because, yeah. So R hat cross phi hat is coming out of the board. That would be our Z if we were in cylindrical coordinates. So as long as we're writing a vector, we have to say that's the Z hat. Okay. So that's the expression of this vector. And of course, it's perpendicular to the XY plane as I've defined it here. So now we have that, and of course now we have the magnitude in plane polar coordinates. So plane polar coordinates, L is equal to M R squared phi dot Z hat, which we're pretty much going to dispense with after this, but we're looking for the magnitude, and R squared phi dot is the magnitude. So if we were to return to this whole list of properties now in our central force problem, right, we've got Newton's law, we've got conservation of energy, we have conservation of angular momentum, which allowed us to use plane polar coordinates, and we now have this expression for, I'll put a box around both of them. But in particular, this second one here is the one we're going to be using a lot. We already used this one, you could say, by going to plane polar coordinates. I better consult the clock. Consult the clock. Oh, yes. So I think I'll wrap it up. This is a good place to wrap it up. It's an amazing theory, okay? See how it systematically just unfolds? Maybe well, you have it all there. Maybe you should gather all of these results. Here's what I'll do, I'll write what we're going to do next. Next, we have to express the energy in terms of plane polar coordinates. Where's the energy? The energy is right here. The R dot is right here. Okay. So next, express energy, E, in terms of the plane polar coordinates. That's going to be our strategy for solving these types of problems. It's going to be to express the energy in terms of the plane polar coordinates. What we're going to find is this L is going to come into play as well. In fact, I'm just looking at it, I think I'm going to turn it into a lowercase l next time. Because if we express everything in terms of plane polar coordinates, including the energy, then we've reduced the order of the differential equation. Remember, second order, it'll be a coupled first order equation, and that's how we're going to tackle it. Okay, this was a great amount of progress, so just go ahead and write this down, make sure you understand every step we took, and see you guys next time.